Okay, so at the end of the last video, we compared the two example problems where we had our mass spring damper system, and with the mass spring damper system, we were able to find that both situations, regardless of what the inputs were, ended up with the denominator of our system having s plus 2, s plus 3 to represent it. And we want to be able to talk a little bit more about systems and see what's in common. So we're going to introduce a new term today, and that term is going to be the poles. And, sorry, I am still remembering how to use the software. So, the poles of the system are a way to describe one aspect of how the system responds. And so let's say that we have the system. It can mathematically be represented in the Laplace domain of some numerator of s over the denominator of s. So previously, in the last example, it was 2s plus 11 over s plus 2, s plus 3. Poles are the factors of the denominator of the system. So they are the solution for setting that den of s, denominator of s, equal to 0. And we're going to see more about how they respond, how they're important, because as we go through the course, for now we're just going to say that they are important and look at different types of poles, because we're going to see that there's slightly different types. So a pole is going to tell us how a system responds, and there's 3 patterns that we can see. The first one is going to be real poles. Now, real poles are the ones that we've seen before. So let's say we have a system that's represented by x of s is equal to 3 over s plus 2. The pole would be the solution of setting s plus 2 equal to 0. So in this case, if we set s plus 2 equal to 0, that equation is correct when s is equal to negative 2. So the pole is at negative 2. There is one pole in this scenario. You could have multiple poles that are real, but in this case it's just one pole. Now, there are repeated poles. So repeated poles is where you have multiple poles at the same point. So if we look at 3s plus 5 over s plus 2 squared, that is not an equation that you're going to be able to find on the Laplace transform table. And again, for the ease of the video, I don't have the Laplace transform table here, but I'll show it on the next slide. But take my word, that's not on the Laplace transform table. We're going to have to split it in 2. So we're going to have one numerator over s plus 2. So there we have one pole at negative 2. And then we're going to need to have a number over s plus 2 squared. So what's going on here is we have real poles, but there are 2 poles, and both of them are located at negative 2. And so that would be a repeated pole. And I'll show you what these are on the Laplace transform table and what they mean for a system response. Finally, there are complex conjugate poles. So complex conjugate poles would be a plus, so some real number plus or minus a number times I, or times an imaginary number. So I told you that we are dealing with complex numbers. Here they're coming into play, and they will always come in pairs. I realize I've been pressing the wrong button. Oh well. So they always come in pairs. Always 2 there are, no more, no less. A positive master and a negative apprentice. And so an example of this might be, we might have x of s is equal to 1 over s squared plus 8s plus 25. If you want to go ahead, try on your own, you could press pause here and do the quadratic equation. I guess do pause here now. And if we do that, we're going to find that the pole is located at negative 4 plus or minus 3i. So we can rewrite this equation as x of s is equal to 1 over s plus 4 squared plus 3 squared. So that would be s squared plus 8s plus 16, and then plus 9, which is the same equation. So it's all real numbers in terms of the denominator, but the poles exist only with complex values for s. Now, if we put in the Laplace transform table, then we can see where these poles show up. So first example was real poles. Those are e to the at or negative at, depending on what they have. Here's an example system where everything is negative. Repeated poles, we saw that the first time a pole repeats, it's just treated as that line e to the at or e to the negative at. Once you start repeating, you're going to be using this equation where it's going to be e to the at times t to the n, where n is represented by how many times you've raised the power. So n would be equal to 1 for our example because we only had 2 repeated poles. It starts to increase depending on how many times you have a pole at the same spot. And complex poles are going to result in functions of e to the at times sine of bt. So if you think about a mass spring damper system, the one that we talked about would slowly shut and there wouldn't be any oscillation. But if we had a stronger spring, we could have oscillation until the damper eventually wins out and the mass stops oscillating. And then we would have seen complex poles in our system set up. So those are the types of poles. Next equation, we're going to start to learn some cool things we can do with poles. Next video, we're going to do some cool things with the poles. And then in our next week in class, or in the next video after that, where time has no meaning, then we're going to start learning about transfer functions, which is a way to discuss systems without discussing the inputs. And I will see you there.